Good evening and welcome back to Dr. Logic Awkwardly Does Logic, and in this time gives you 4 different definitions of consistency. Now, in the context that we're going to be working in, all of these definitions are going to end up being equivalent to each other. However, this is because we are working in a classical modal setting. That means we have the law of excluded middle and the principle of non-contradiction. If we don't have either or both of these principles, then the notions of consistency that I'm going to define can come apart. And there's huge fields of logical research on what types of systems have what types of consistency. As a result, it's important, or at least it's interesting for me to mention these other types of consistency at this point so that you've got kind of the fuller picture, know a bit more about what the options are. As I said, these notions of consistency are all going to end up being equivalent to one basic one that's going to be the one that we use the most. But sometimes it can be useful to use one of the other versions of consistency. They're all equivalent in our particular context, so we know that we can. And sometimes having equivalent formulations of the same concept can be really useful in terms of finding different ways at going about solving problems. So I'll give you first the main definition, the one that is going to be kind of the central core definition that we use. And that is something that we've seen before. So the definition of consistency is actually going to be consistency with respect to a particular proof system. Because this notion of consistency is not semantic consistency, but proof theoretic consistency. So we'll just add a little parenthetical here. So this is consistency with respect to a system S. So what we will say is that if we have given an axiomatic basis S, and of course, some proof system that is, kind of grows upon this, we will say that a set of well-formed formulas lambda, I'm not sure we've ever had lambda before, or at least not in a long time. This symbol here is a capital lambda. It's often used to indicate a set. So we have a set of widths lambda is going to be S inconsistent if and only if there is some finite subset of this set lambda. So there is a finite subset, let's call it gamma, and gamma, because it's finite, we can number the list of we can number each of the formulas that are in it. We can turn it into a list. So gamma contains phi 0 all the way up to phi n for some n, and it's going to be a subset of lambda. Now, lambda itself could be infinite. It could also be finite. Gamma could be identical to lambda if lambda is finite. Doesn't really matter. All that we know is that we have some particular subset, phi 0 to phi n, such that in this particular proof system, you can prove the negation of the conjunction of all of them. So take the conjunction from phi 0 to phi n, and if you can prove the negation of that, then you know that that particular set of sentences is going to be S inconsistent. So in the system, it is possible to prove the negation of the conjunction of some subset of the set. Now, this is the definition of inconsistency, but what we want is consistency. Consistency just is the opposite. So if this is not possible, if there is no finite subset that you can prove the negation of the conjunction of, then lambda is consistent with respect to system S. A stronger system might make that system inconsistent. It could be that there is some sort of contradiction lurking in the system or in that set, but our system is just not strong enough to be able to prove it. The interesting thing about this definition is that there is a crucial connection between consistency of every finite subset and consistency of the set as a whole. So if you know that every finite subset is consistent, this will propagate up to the consistency of the entire set, even if lambda is infinite. The reason why this is the case is because all of the proof systems that we are looking at in our particular context are finitary. Every proof is going to be some finite number of things. So you will never have an infinite conjunction because you could never write that infinite conjunction down. So this is our primary definition of consistency, but I'm going to give you a couple of other definitions as well. So more definitions of consistency. So we might also want to say that to speak about kind of the consistency of a particular system, as opposed to the consistency of a set of formulas with respect to that system. So this is another reason why showing that these definitions are equivalent is useful, because then we can talk about consistency of sets or consistency of systems interchangeably as we want. So we have here a notion of, so a system S is going to be absolutely consistent. So that's the notion of consistency that we are defining. If there is some well-formed formula phi such that this formula is not provable in the system. So you've got an absolutely inconsistent system if you can prove everything. But if there's at least one thing you cannot prove, then your system is absolutely consistent. Another notion is a notion of atomically consistent. So this is sort of a special type of absolute consistency, or kind of a related notion. So if we know that there is some formula that it cannot prove, then it's absolutely consistent. Atomically consistent is if there is some atom, call it P, such that this system does not prove the atom. So all of the systems that we've looked at so far are going to be atomically consistent because they don't prove any atoms. So it's not just that there's one that it doesn't prove any of them. Something you can immediately see is that every system that is atomically consistent will be absolutely consistent, because atoms are well-formed formulas. So if you don't prove an atom, there is some well-formed formula that you do not prove. And finally, we have a notion of negation consistency. So a system S is negation consistent if you can't prove both a formula and its negation. So if it is not the case that in system S you can prove phi, and in system S you can prove not phi. Now, negation consistency is the really interesting notion of consistency when you start looking at non-classical logics, because these are often ones where negation is not just the dual of truth. So you can have systems such as intuitionistic logic where negation is a stronger notion. So it's not just that it like fails to be true, but in an intuitionistic setting, it not only fails to be true now, but it will never, ever, ever be true again at any point in the future. So once you pull negation apart from simple failure to be true, then all of a sudden, phi and not phi are no longer duals of each other. And therefore, it's relevant to speak of systems where there's a notion of consistency that says, even if these two are not duals of each other, we don't want to have both of them in the system at the same time. So here are 4 definitions of consistency. And I think I'll draw this video to a close. And in the next one, what I'm going to do is just sketch to show how these different definitions imply each other or are equivalent to each other. And this, as I said, will allow us to be able to use whatever notion, whatever definition we want in a given context to see, whichever one is the easiest one to use, that's the one to use. But we'll save that proof for next time. Until then, take care. See you later. Cheers.